All right, now we come to the third part, which is dealing with series and parallel circuits. Now when it comes to dealing with series and parallel circuits, you can take the same elements and do various different series parallel combinations, and lo and behold, they will be different with each potentially different configuration. So the reality is whenever you're dealing with series circuits, you have to make sure that you keep track of how you got from one stage to the next. And we'll talk about that as we demonstrate. Now, our key saving grace is, one, Ohm's law still applies, so that's good. And note also, when it comes to calculating the total power of the circuit, remember in a series circuit, we could simply find the power in everything, make sure it equals total power, we're good. In a parallel circuit, if we found the power in all the elements, added them up, and it equaled the total power, we were good again. And that is still true when it comes to the power of a series parallel circuit. The total power of a series parallel circuit is going to be equal to the sum of all of the series parallel combinations. Now, the one thing you have to make sure is that when you do your combinations, that you need to take all of your resistors and simply end up with either a series circuit or a simple parallel circuit when you start analyzing it. Now, the key is redrawing at every single stage. Don't go and think you're going to remember how you got from stage 1 to stage 2. It's kind of like going into a cave. If you don't have the string to get you back out on the right path, because all things will look the same, you will get lost. So, follow me. Make sure we always make sure that Kirchhoff's voltage law, Kirchhoff's current law, and the power all sum up at the final ending stage. Here we go with our circuit analysis. Now, how can we tell if things are in series or in parallel? Well, one, typically when we're going to find our total resistance in redrawing, we typically want to go furthest away from the source. Note R4 is furthest away from the source. So we can see that that is directly in parallel, so they share the same voltage. There's no resistors here. We're good. So we would say R3-4 combination is going to be equal to R3 in parallel with R4. So we find the combination of that resistance simply by saying 1 over R3 plus 1 over R4, which is 1 over 6K ohms plus 1 over 6K ohms, which gives us 3K ohms. So now we want to redraw with this information. So I go over here and I say, okay, my 12-volt source has not changed. I still have R1 here, and that's still 12K ohms. And we still have the 9K ohms of R2. And now we replace this connection with the newfound R3-4 value, which is 3K ohms. Now, we see that we now have one complete path. So this is a simple series circuit. So we can find the total resistance by combining R1 plus R2 plus the R34 combination, which is 12 k ohms plus 9 k ohms plus our combination of 3 k ohms. And that gives us a total of 24 k ohms. So we can say, all right, we got 24 k ohms, woohoo. We can write that down, and because we're just going to look at this circuit, we're not going to look at the whole thing yet, just this circuit, and do an analysis of it. So if we do an analysis of it, we find our total current by taking 12 volts divided by 24 k ohms, and that gives us 500 microamps, not milliamps, but microamps. Okay, so we can say, all right, we got 500 microamps going here, we got 500 microamps going there, we got 500 microamps going through here, and 500 microamps going through there. So since R1 and R2 are already sitting there by their little lonesome, we can go ahead and say, okay, we've got 500 microamps and 500 microamps. And of course, what law can we apply? That's right, Ohm's law. So we can say that 500 microamps times 12 k ohms gives us 6 volts, and 500 microamps times 9 k ohms gives us 4.5 volts. So I'm going to go ahead and write that on here. We've got 4.5 volts here. We've got 6 volts there. And remember Kirchhoff's voltage law. It said that all of these voltages have to add up to that. So we could apply Ohm's law just for this 3 k ohm resistor. We would say, okay, for the R34 combination, we would say 500 microamps times 3 k ohms gives us 1.5 volts. And indeed, that 1.5 plus 4.5 plus 6 adds up to 12. Now, so I'm going to take the information we found out down here, because we said, all right, we got 500 microamps going through here. We got 500 microamps coming back and going through here. Now, we said we found this to be 6 volts, and we found this to be 4.5 volts. Now, these two came from them being in parallel. What do things in parallel share? You got it. They share voltage. So, the voltage across R3 and R4 is both going to be 1.5 volts and 1.5 volts. So I'm going to go ahead and write 1.5 volts here and 1.5 volts here. Now note, 1.5 volts divided by 6 k ohms equals 250 microamps. And 1.5 volts divided by 6 k ohms gives us 250 microamps. Now we aren't surprised, because if we have 500 coming in, we have two equal value resistors. It's going to split evenly and give us 250 microamps in that branch and 250 microamps in this branch. So now if we apply our power, so if we take 6 volts times 500 microamps, that gives us 3 milliwatts, and 4.5 volts times 500 microamps, which gives us 2.25 milliwatts, and 1.5 volts times 250 microamps gives us 375 microwatts, and 1.5 volts times 250 microamps gives us 375 microwatts, and our total is going to be 12 volts times 500 microamps, which is 6 milliwatts, and 3 plus 2.25 milli and 375 micro and 375 micro add up to 6 milliwatts. So we're good on the power. Note, at no place in time have we violated Kirchhoff's voltage law, because remember, since we come through here, if we go through that complete path, it adds up to 12 volts, or if we go through this complete path, it adds up to 12 volts. Now, we have 3 resistors. Now, the key for series parallel circuit analysis is what things are in series and what things are in parallel with each other. Now, a lot of people would physically look at this and they'd say, okay, 18 and 6 are in parallel with each other, but we got a problem with that. And the problem with that is the fact that we have this 12K ohm resistor that is in the way. Note that R2 and R3 share the same current path, right? So they are in series. So what we're going to do, we're going to start with the resistor furthest away from the source, and we're going to say, alrighty, let's go ahead and say that we're going to redraw this, because R2 3 combination is going to be equal to R2 plus R3. And we're going to go ahead and add those up, and a 12 ohm resistor and a 6 ohm resistor add up to being 18 ohms. And I am going to redraw this circuit. So instead of trying to analyze everything here and remember how I got there, I'm going to say, okay, I'm going to redraw this, and I'm going to say, all right, we've got a 4.5 volt voltage source. We still have R1 sitting here. So R1 is still 18 ohms. And we have R2, three, which is 18 ohms. And these are in parallel with each other. So the total resistance is equal to 1 over 18 ohms plus 1 over 18 ohms, which gives us 9 ohms. So we can simply analyze this circuit. So if I do so, I can say, all right, I've got 4.5 volts here, 4.5 volts here, and we can say our total resistance is 9 ohms. Our total current is going to be 4.5 volts divided by that 9 ohms. And that gives us, so let's go ahead and get the calculator out. So always helps to turn it on. 4.5 divided by 9 gives us 500 milliamps. So 500 milliamps, and I'm going to go ahead and draw that right on here. So we got 500 milliamps here. We know that our R1 is sitting here all by its little lonesome. So we can go ahead and say we've got 18 or I'm sorry, we've got 4.5 volts here. And our 4.5 volts divided by 18 ohms gives us 250 milliamps. And this one is, oh, well, we can't do that one yet, because remember, this one is a combination of these two. So we've got 250 milliamps going through this branch. How much do we have left to go through this one? Well, how about that? Half of that, which is 250 milliamps. So if I go and draw this up here, I know that this is 4.5 volts, 500 milliamps. We've got 250 milliamps here, and remember that current is also going to be shared by R2, which is 250 milliamps here. And we can go ahead and write that down because these two are in series, so 250 milliamps and 250 milliamps. If we use Ohm's law and 250 milliamps times 12 ohms, well, let's go ahead and calculate. And that gives us 250 milliamps times 12 gives us 3 volts, and 250 milliamps times 6 ohms gives us 1.5 volts. Now, if we go ahead and calculate the power, 250, or I'm sorry, let's do that again, 1.5 volts times 250 milliamps, 1.5 times 250 milli equals 375 milliwatts, and 3 times 250 milli gives us 750. Gives us 750 milliwatts, and 4.5 volts times 250 milli gives us, so 4.5 volts times 250 milliamps gives me 1.125 watts. And our total power should be 4.5 volts times 500 milliamps. So 4.5 times 500 milli gives us 2.25 watts. So let's make sure that these add up. So 750. So 750, milli plus 375 milli plus 1.125 gives us 2.25 watts. So that one looks good. Okay, and we just got started having fun. Here we go, another circuit. Now we have 1, 2, 3, 4, 5 resistors. Now remember, when we're going for the combination, we basically want to go furthest away from the source. So we start here at R4, but we look that we can't directly say it's in parallel with R2 and R3 because these two are in what with each other? Well, they share the same path, right? So these two are in series. So our first combination is going to be the R2,3 combination, which is going to be R2 plus R3, which in our case here gives us 1.2 k ohms plus 1.8 k ohms, which gives us 3 k ohms. Now we're going to redraw the circuit. So the next time we draw it, I'm going to say, okay, we've got our 120 volt source here. So, whoops, 120 volts. And we have our R1 of 1.5 k ohms. We still have R5 down here as our 1 k ohm. And then we have the R2,3 combination, which we found to be a 3 k ohm resistor. And then we have our R4 combination, which is a 15 k ohm resistor. Now, if we look, we see now that this combination and R4 are both directly in parallel with each other. So I like to come up with a new crazy name for this combination. I call it the R2,3,4 combination, which is going to be equal to R2,3 in parallel with R4. So we do 1 over 3 k ohms plus 1 over 15 k ohms. And let's go ahead and calculate that so we don't make any mistakes. So 1 divided by 1 divided by 3k. Oh. Plus 1 divided by 15k. And we get 2.5k. So that R2,3,4 resistor is going to be 2.5 k ohms. So we're going to redraw our circuit here. So we've got our 120 volts. R1, which is 1.5 k ohms. And then we have our R2,3,4 combo, which is 2.5 k ohms. And we have R5, which is 1 k ohm. And that leaves us with a simple what circuit? You're right. It leaves us with a simple series circuit. So we can find the total resistance is equal to R1 plus the R2,3,4 combination plus R5, which gives us 1.5 k ohms plus 2.5 k ohms plus 1 k ohm, and 1 plus 2.5 gives us 3.5, which gives us 5 k ohms. So we can go ahead and write this down of 5 k ohms. And we can say, all right, we can find the total current now. And we apply what law? That's right, Ohm's law. So 120 volts divided by 5 k ohms gives us 24 milliamps. Now, so that means out of here, we got 24 milliamps. That means we've got through here 24 milliamps. We have going through here 24 milliamps. We have going through here 24 milliamps. So we can say, well, R5 is sitting by itself. R1 is sitting by itself. So I can now say I've got 24 milliamps here and 24 milliamps here. And I can apply Ohm's law to find the voltage. So 24 milliamps times 1K ohm equals 24 volts, and 24 milliamps times 1.5K ohms gives us 36 volts. Okay, so I'm going to go ahead and write that right on. So I've got 36 volts here. I've got 24 volts here. Now we know that these all have to add up to 120. Now I can say that 24 milliamps times 2.5K. So let's just go ahead and do that. So I'm going to write it down here. So our voltage across the R2, 3, 4 combination is going to be 24 milliamps times our combination resistor, which is 2.5K ohms. And if we calculate that, we're going to go ahead and do that together. So we've got 2.5K ohms times the 24 milliamps, and lo and behold, that gives us 60 volts. So if we look, now that makes it 60 volts there. Now let's take the information that we found here and put it back here. Note, these two were found by these two being in parallel. And because they're in parallel, it means they share the voltage. That means we're going to have 60 volts here and 60 volts here. So once again, we're still going to have 36 volts here, and we got 24 milliamps going through there, 24 milliamps going through here, and 24 volts here. So that means between these two, so if I take my 60 volts, because R4 is sitting there by itself, so I can say, okay, I got 60 volts there, and I can apply Ohm's law, so 60 volts divided by, and this looks like it's a 5K ohm resistor. So 60 volts divided by 5K ohms gives us, oh whoops, not 5, how about 15? That's a big difference there. By 15K ohm resistance gives us 4 milliamps. That looks a little bit better. So that means if we've got 4 milliamps going this way and we got 24 milliamps coming in, how much do we have left here? Yeah, that's right, it's 20 milliamps, which we could also find by taking our R23, so the current in R23 combination is the 60 volts divided by the 2.5K ohm resistance, or I'm sorry, the 3K ohm resistance, which is 20 milliamps. Now if we take that information back to here, so let's go ahead and write down what we've got. We've got 24 milliamps going here. We've got 4 milliamps going here. We know we have 20 milliamps going there. And since these are the same path, that means we've got 20 milliamps going through here as well. And we have 24 milliamps going through there. We know that this is 60 volts. We know that this is 36 volts. We know that this is 24 volts. So can we find So since we now know the current is 20 milliamps through both of these resistors, we can apply Ohm's law to find the voltage for each one. So with R2, it's 20 milliamps times 1.2K, which gives us 24 volts, and the 1.8K, so we get 20 milliamps times 1.8K, which gives us 36 volts. Note that if we say this one is 24 volts here, and this one's 36 volts here, 24 plus 36 add up to 60, right? That's one closed path. And that 24 plus 36 plus 24 plus 36 all add up to 120. So at no point in time is Kirchhoff's current law, because we got 20 and 4 add up to 24, or Kirchhoff's voltage law, 24 and 36 add up to 60, right? In that closed path, we are doing good. So let's make sure that our power is all copacetic. So here we've got 24 volts times 24 milliamps, and that gives us 576 milliwatts, and 60 volts times 4 milliamps gives us 240 milliwatts, and here we have 36 volts times 20 milliamps gives us 720 milliwatts, and 24 volts times 20 milliamps gives us 480 milliwatts, and 36 volts times 24 milliamps gives us 864 milliwatts. And when we calculate our total power, it's going to be 120 volts times 24 milliamps, which gives us 2.88 watts. And if we add up 864, 480, 720, 240, and 576, lo and behold, they end up being 2,880 milliwatts, which is 2.88 watts. Yay! Simple and easily done. Well, it's really not too bad as long as you keep track of going from each step along the way. Oh, okay. Our last one, dear. We're good? Mm-hmm. All right. Yay. One more. Because, you know, we haven't had enough fun with series parallel circuits. And this looks like a bit of a mishmash here, but let's see what we can do. First and foremost, by golly, I'm looking here, we don't even have a voltage source. Does that mean that we're in trouble? No, not necessarily, because of the fact that here we have the known voltage of 30 volts being found across resistor 2. So we already have that listed right here. Now, if we're looking for the total resistance, we know all of the resistors. So let's look. A lot of people would say, well, you know, 6.8 parallel, got a problem. These all share the same path, right? So if we're doing our combinations, we would say we have R3, 4, 5 combination, and that is in series of R3 plus R4 plus R5, which is 1.2K ohms plus 6.8K ohms plus 12K ohms And that adds up to, well, let's go ahead and put our little calculator in here. Okay, so let's do 1.2 K plus 6.8 K plus 12 K, which gives us 20 K ohms. And of course we want to redraw. So we'll go ahead and do that. And I'm going to go ahead and draw it down here so we have a little more space to do so. So we have our voltage that we don't necessarily know what it is yet. We still have R1, which is a 1.8 K ohm resistor. We have R6, which is a 2.7 K ohm resistor. We still have R2, which is a 12 K ohm resistor, and we'll write that down here in just a second. And then now we have the R345 combination, which is 20 K ohms. Now, I'm just going to write this down because we know it from here that the voltage here is 30 volts, because we know that from this drawing. Now, we're still looking for the total resistance. We see that R2 and the R345 combination are in parallel with each other. So if we go to our next stage over here, we say that R2 is in parallel with the R345 combination, and so the R2345 combination is going to be 1 over 12 K ohms plus 1 over 20 K ohms. And to make sure we don't make any errors, let's go ahead and do that on our calculator. So we have 1 divided by 1 divided by 12K plus 1 divided by 1 divided by 20K. And that gives us 7.5 K. So we've got 7.5 K ohms. And we're going to take that information and draw it over here. So we still have our voltage source, and we have our R1 of 1.8 K ohms. We have our R6 of 2.7 K ohms. And then we have, last but not least, our R2345 combination, which is a 7.5 K ohms. And when we find the total resistance, then it is going to be R1, since these are all in series, R1 plus R2345 plus R6, which is 1.8 K ohms plus 7.5 K ohms plus 2.7 K ohms, which equals, well, let's go ahead and add it up. Let our fingers do the calculating. 1.8 plus 7.5 K plus 2.7 K. And that gives us a total of 12 K ohms. So we can write this down of 12 K ohms. Now, That being said, remember over here we said that this was 30 volts, and since these two are in parallel, we know that we're going to end up with 30 volts there, but we also know that we've got 30 volts here. So because we have 30 volts here, we can say, all right, we can apply Ohm's law, and 30 volts divided by 7.5 k ohms gives us 4 milliamps. So that means that if we've got 4 milliamps going through here, that means we've got 4 milliamps going through there and 4 milliamps going through there. So if we said that now that is going to be our total current, so we've got 4 milliamps there, R1 is 4 milliamps, and since R6 is sitting here by itself, it is also 4 milliamps. So we can apply our Ohm's law with R6, and we can say that 4 milliamps times 2.7 k ohms gives us 10.8 volts, and 4 milliamps times 1.8 k ohms gives us 7.2 volts. Oh, that was easy. Okay. And because we know we have the 30 volts here and here, right? And we said how much is the current? Well, the current coming in here is going to be 4 milliamps. Current going out here is going to be 4 milliamps. We can say, all right, this is by itself, so 30 volts divided by 12K. So 30 volts divided by 12 k ohms equals 2.5 milliamps. So if we've got 2.5 of that going through here, how much is left to go through here? Well, got to be 1.5. Because 1.5 and 2.5 add up to 4, but lo and behold, if we take 30 volts, divide it by 20 k ohms, it equals 1.5 milliamps. So, we know that this came from them being in series. So, let's go ahead and draw what we know on this last diagram. So, we said, all right, we had 4 milliamps here. We now know we have 2.5 milliamps going through here. How much is left to go through here? 1.5 milliamps. Since it's the same path, it's 1.5 milliamps and 1.5 milliamps. They join back to the 4 milliamps here. We had said also that we had R1 has a voltage of 7.2 volts. R6 we said is 10.8 volts. We've got 30 volts here, and 7.2 and 10.8 plus 30 gives us 48 volts. Cool, huh? Of course, it's the same thing down here, 48 volts and 48 volts. Now, then we find out, we say, okay, we've got 1.5 milliamps here, 1.5 milliamps here, and 1.5 milliamps here. We then find the individual voltages by applying Ohm's law. So with R3, it's 1.5 milliamps times 1.2 k ohms, which gives us 1.8 volts. And 1.5 milliamps times 1.2 k ohms gives us 6.8. Use the wrong value of resistance there, 6.8, which gives us 10.2 volts. And last but not least, the 1.5 milliamps times 12 k ohms, which gives us 18 volts. Now let's take a quick gander here. If we've got 30 volts here, and we said that we had 1.8 volts there, and we had 10.2 here, and we have 18 volts here, 1.8, 10.2, and 18. Oh, by golly, they add up to 30. We're doing good. We're doing good. So last but not least, we want to do our total power. So we said we found this to be 48 volts. So our total power of 48 volts times 4 milliamps gives us a total power of 192 milliwatts. If we go ahead and calculate them, so we've got 30 volts times 2.5 milliamps, which gives us, for the second one there, well, let's just go ahead and calculate it. I believe it should be, oops, 30 times 2.5 milli, which gives us 75 milliwatts, and 1.8 volts times 1.5 milliamps gives us 27 milliwatts, and 10.2 volts times 1.5 milliamps gives us 15.3 milliwatts, and 1.5 volts times 18 volts times 1.5 milliamps gives us 27 milliwatts. I'm sorry, this was 2.7, my bad. That's what happens when you use the DNA calculator. And then last but not least, we have 10.8 volts times 4 milliamps, which gives us 432 milliwatts. And if we add all of those up, if we take 75, oops, we kind of forgot this last one here. So 4 times 7.2 gives us 7.2 volts times 4 milliamps gives us 28.8 milliwatts. If we add these up, they come up to 192 milliwatts. And that concludes our series parallel combinations.